Yes. So the abstract that we are presenting this year to ISMRM is titled like Layer-fmri at 0.39 millimeter isotropic meets vascular mapping at 0.35 millimeter isotropic. Partners or confounders. So this is a collaboration between Maastricht, so me, Farouk, and Breiner, and together, of course, with Renzo in MGH. So the motivation behind this abstract is try to understand better the physiological origin of the Layer-fmri signal that we can get with the bold contrast. Layer-fmri community is growing and growing in the last years, and is actually a very important tool for investigating cortical circuitry in non-invasive way in humans. However, nowadays the spatial resolution is still insufficient to fully resolve laminar activity if we consider the gold standard with 0.8 millimeter isotropic. And as a result, we always see that laminar fMRI results are very variable across subjects. And all this basically it's hampering the interpretability and the relevance of Layer-fmri for understanding how the brain works in terms of cognitive neuroscience, but also in clinical application. So what we want to do here, we want to present a new protocol that increases the Layer-fmri resolution beyond 0.8 and reach to 0.39 millimeter isotropic. And we would like to assess how much the vasculature can contribute to the laminar bold variability. So how much of it can actually predict the laminar profile that then we can observe. And to do that, Renzo developed a new protocol that allows us to reach this 0.39 with a bold contrast under the Frisco approach that he just explained. And we paired this acquisition with a multi-echo 3D PI T2 star images for getting a proxy of mesovein imaging. We further developed some analysis tools that allows us to merge together these two acquisitions and to look how the laminar profile can be analyzed in terms of local vasculature. So here, my figures are pretty dense. Sorry about that for abstract limits, but so this is basically an overview of how the Frisco data look like at 0.39. So we could actually get a very nice CSNR map to compute the mean of the EPI. We can see very interesting features such as like the layer 4 or some intracortical veins by naked eyes. And Renzo achieved this by a specific skipped CAIP readout scheme that decreases a lot the amount of ghosting while keeping the best of the image quality. In the lower part of my figure, I'm showing you a group result, a single subject activation map. So we collect data from 6 participants while they were exposed to just a flickering checkerboard. We preprocess that and then we compute statistical map as a t-value. Okay. And what was astonishing for us was to see that first we get very nice activation, see both positive and negative. And this is very consistent as I'm pointing with my cursor, that I hope you are seeing it, in the negative side, but also the positive activation literally overlapping with a layer 4 in some pieces of the cortex and many more features. So as I said, we paired this acquisition with an anatomical acquisition that is T2 star, that give us at the end the T2 star weighted images. These are the result from single subject. And we exploit this acquisition also with the analysis methods that we use. In particular, we did use a volume render that allows us to pop up the vasculature quite a bit, both in the pial surface by using a very specific braid mask that we call here leptomeningeal mask, but also while playing with the contrast, we can also see intracortical vessel. Okay, so here what I'm showing you is the overlay of the functional activity of one participant on the T2 start weighted images at 0.35 millimeters. And you could see, hopefully, you could spot that there is something interesting going on along the calcarine sulcus. So there is negative T values going through the calcarine. and is surrounded by a positive activity. So we were quite interested in following this, and we did reconstruct all this negative activity in 3D. So we manually labeled and reconstruct, and it interestingly looked like a vessel or looked like a tube. And now we need to understand where this tube come from. Is it a vein or is it an artery? Unfortunately, the acquisition that we did use doesn't allow us to, by contrast, differentiate arteries from vein. However, what we did here, we basically referred to the gross anatomy. We used Overnoy information from the human brain stem, and we could manually segment the artery from the brainstem, reaching the visual cortex. And we could clearly see that this artery from the brainstem is meeting with this negative activity that I showed you before. And then we can discuss why this is happening. We did want to do a step forward, therefore we took this activity and we compute geodistance to try to understand how much or how big is this extent. And we figured out that, for instance, in one participant is 32.5 millimeters. So it's really like going within the calcarine sulcus for quite an extent. So if we assume that this is an artery, it is bringing like new blood that is modulated by the task in a specific way. So in all the gray matter that is surrounding this vessel, we would expect to have interesting activity. To define this area, we basically extend this geodistance measure that we compute within the tube to the gray matter so that we could wrap it around. And we can use this as a way of parcellating V1 according to the geodistance. So now the geodistance is here on the top part as an x-axis on this plot. And in here I have stacked three different plots. The first one is 1 divided T2 star weighted signal, so from our anatomy as a reference. Then I have the 0.39 millimeter, so the new functional data. And then as a reference, we also collect some 0.8 for our subject. And each columns of this is the parcellation of V1, what I showed you here. And you can imagine that is even more fine. So I bin this piece of the cortex with 900 columns. So, so each of these, even if it's very thin, it represents a substantial piece of the cortex. And like what was astonishing to me was that we see a lot of variability in the laminar profile. So on the y-axis, it's always presenting cortical layers from deep to superficial. And if we focus, for instance, on the middle here, you see that there is every kind of laminar profile you want to find in your data. There is a decrease, there is an increase, there are like columns and so on. And of course, all this variability or variance that is much bigger compared to 0.8, you wouldn't catch it if you would summarize all your laminar profile with just a line plot. And here I'm showing this as a median, as it's more resistant to outliers and just one standard deviation. And it's the same scale, so you can already appreciate how much variance is within this higher resolution data compared to conventional 0.8. Then what we did, we try basically to find template in this horizon or multiple layer profile. We pick up 4 in particular. So one that shows a linear decrease from deep to superficial layers. For instance, these columns that is highlighted here. And we try to understand why there is like negative T values on the superficial layers. Well, if we extended a little bit our segmentation above the gray matter and we include the pial surface and we rendered the vasculature behind from our anatomical images, as I showed you in the beginning, and we overlay with the fMRI activity, we could clearly see that this negative activity is following the artery that we previously labeled. So this is actually why we are seeing this pattern. The second pattern, laminar profile, is a linear increase. So what is very much discussed as a brain-in-vein effect in the Layer-fmri community. So it's a linear trend between the deep layer to the superficial layers. And here it's highlighted in green bins here. For instance, you see there is a very bright spot in the anatomy, that is already an indication of a vasculature there. So we did the same. So we extract the pile surface above the gray matter, we render it, and we overlay with our activity. And we could again explain that this positive trend, linear increase, is due to the fact that the blood is going through this pile big vein. Interesting, we also find something, some activation, some profile that we couldn't relate with any vasculature structure behind. And for this, I'm talking about the conventional, what is known as middle layer peak, that is highlighted here in these red columns. And maybe it can be our resolution, but there is nothing that we could clearly relate to it in terms of vasculature, but only the layer 4 stria that is visible there, and the signal looks like it's following this stria. And lastly, we also have like some layer profile that are almost flat. They don't show any modulation. And in that case, when we went back to the volume, that was our best way of visualizing this effect, we do see that there are indeed like some intracortical vessel, and our positive activity is flat and always the same within this vessel. Overall, we did quantify that for this participant, 51% of the layer profile could be actually predicted by the anatomical underlying with T2 star, as I think we would expect. So with this, I'm just concluding, and we hope that in the future we will be able to link even more these two data type and improve our understanding of the laminar cycle. Yes.
Nice. So the hypothesis now is that like, why are arteries negative? The idea is that the intravascular signal is dispersed, and then you have an arterial blood volume dilation effect.
Yes, that's like, I think, the current understanding, due to the blood motion artifact, like the signal from the artery is like traveling away, let's say, even during multiple echoes. If you have like a multi-echo acquisition, it's like clearly moving, but this is happening within our readout in fMRI. And then basically the amount of volume, you can get this CBV increase of the artery, but just because the signal while you have activity is actually less due to partial voluming. So that's why at the end we think that this could be an explanation for this negative statistics that we get.
Yeah. You're saying that you did, yeah. I have time to ask questions later. Yeah.
Oh, okay. No, that's quite interesting, because we see similar stuff, right? Like with some of the smaller PL arteries in vessel-specific fMRI. So I guess my question was more like, in the future, would you like just do a simple multi-echo scan and just make sure that this is actually an artery, and instead of like just validate that what you're seeing is accurate?
So you are saying that one way to actually assess whether what I see is coming from an artery or not will be to have a different acquisition type. Yes, I think with this we are like considering getting collecting some time-on-fly images.
Yeah.
And then we can have a differentiation in terms of acquisition contrast. However, I also do believe that gross anatomy is really clear. I was a bit skeptical, but then looking at the book and like following the artery from the brainstem to the visual cortex, I decrease my doubt on whether it's artery or not quite a lot. Of course, I cannot be sure 100%, but yeah, it was good to see it.
Cool. Yeah, at 34. Divya, do you want to go next?